As we've seen in previous lectures, disinfection systems have fairly severe constraints in terms of the requirements for performance. The performance of these disinfection systems will be influenced by fluid mechanics and mixing, disinfection kinetics, and other reactions that take place within the system, all of which need to be considered in design. In this lecture, we'll consider the contemporary tools that are used to design disinfection systems of various types. Let's start with chemical disinfection systems and consider their efficacy. Generally, the treatment objectives for disinfection systems call for somewhere between 3 and 6 base 10 log units of inactivation. As we've seen several times previously, process performance in these systems will be governed by the combined effects of transport processes, mixing behavior, and the intrinsic kinetics of the reactions that take place within these systems. Because these systems are required to be very efficient in terms of inactivating microbial pathogens, their process requirements mandate efficient hydrodynamics. Specifically, these systems should approach plug flow conditions and also minimize short circuiting and the existence of dead zones. That's strongly influenced by the geometric design of the system, including any internal baffles that may be included. In broad terms, what this implies is these systems should be designed to approach a narrow residence time distribution. We can characterize the residence time distribution function using tracer testing or computational fluid dynamics. When we go to design a disinfection system, oftentimes those designs are based on numerical simulations. Specifically, they will involve the use of the plug flow with longitudinal dispersion model, which looks like this. It's a partial differential equation which describes the dynamic behavior of the system, where N represents the concentration of viable or infective pathogens within the system. The terms within this equation account for transport by advection and dispersion, as well as the effects of the reaction terms. As mentioned previously, tracer tests or computational fluid dynamics can be used to estimate the model parameters. For example, epsilon sub x, this term right here, is the longitudinal dispersion coefficient. Sometimes it is non-dimensionalized using lowercase d, or the dispersion number, which is the ratio of the longitudinal dispersion coefficient divided by the horizontal velocity and the length of the system. The dispersion number is a dimensionless number that relates transport by dispersion to transport by advection. Generally, we want the dispersion number in these systems to be relatively low. And for practical purposes, what that suggests is that the dispersion number should be less than about 0.01. The graph in the lower right illustrates normalized residence time distribution functions for various values of the dispersion number. And we can see that this dispersion number yields a relatively narrow residence time distribution function for dispersion numbers that are less than 0.01, our design objective. So we can simulate these things by computational fluid dynamics. We can also measure them using a tracer test. In a tracer test, what we'll do is introduce a neutrally buoyant, non-reactive tracer, typically as a pulse at the inlet of the system. We'll then monitor effluent concentration as a function of time, then apply principles of mass balance to estimate the dispersion number. And again, the goal of design is to approach plug flow from a practical perspective. That means a dispersion number less than about 0.01. There are other chemical disinfectant contact chambers that have been developed to yield this type of performance. For example, in the context of ozone disinfection, the deep U-tube was developed, and this is a reactor that performs very close to the plug flow condition. Also, because it involves ozone, it has the benefit of yielding a relatively high pressure at the bottom of the system, typically more than 10 meters deep, where we'll experience relatively high pressure, thereby promoting transfer of ozone from the gas phase to the liquid phase. We can also use something like a long straight pipe to promote plug flow conditions, especially when these systems operate in the turbulent regime, which is typical. As I've mentioned previously, computational fluid dynamics is often used to simulate the performance of these systems and as the basis of design. CFD simulations involve the equations of motion and continuity together with a turbulence closure model, and then we can incorporate scalar terms, typically reaction terms, to describe the dynamic behavior of the system. In these CFD simulations, we define on the computer the geometry and operating conditions of the reactor, and these simulations can provide remarkably detailed descriptions of transport behavior and overall process behavior. And because they capture the relevant physics and chemistry that govern the dynamic behavior of these systems, they can be important for accurate simulations of disinfection efficacy. The simulations that are illustrated in these images are for a reactor in which peracetic acid is used as the disinfectant. And the simulations illustrate the behavior of peracetic acid as the disinfectant, as well as the concentration of the pathogen that is the target of disinfection. So this particular example is based on peracetic acid, but it's important to recognize that CFD can be applied to essentially any disinfectant. Now let's consider some of the basic characteristics of chemical disinfection contact chambers. The principles are generally applicable to chemical disinfection systems independent of the disinfectant. Typically, these systems involve long, narrow reactors to approach plug flow conditions. A common configuration is a serpentine reactor because it provides a number of benefits. Specific benefits of these systems include the common internal walls, which reduce construction costs as compared to a single, long, skinny channel. And also these systems occupy a smaller footprint. However, every time we have the water experience a turn in going through these systems, there are dead zones that are developed. And those dead zones are illustrated by the pixeled areas in the two images on the right. For a given rectangular geometry of the outside of this contact chamber, what we learn from this is that designs that involve relatively few long channels are preferred to those that involve relatively short channels that have lots of turns. Again, the idea here is to minimize the existence of these dead zones. Now let's consider UV disinfection systems. These systems are characterized by strong spatial gradients in local fluence rate. What that implies is that there are going to be equally strong spatial gradients in local photochemical reaction rates, and that's because photochemical reactions depend on the fluence rate. It's not uncommon in these systems to see variations of fluence rate and therefore reaction rate on the order of 10 to 100 times over small distances like 5 to 10 centimeters. That's evident in the image on the right, which is a simulated fluence rate field for a real UV disinfection system. And here we see that the variation is about a factor of 10 over that sort of distance. Also, these systems operate in the turbulent regime in almost all cases. If we consider the fate of a microorganism as it goes through the system, there are many different trajectories that could be taken. For example, if a particle takes a trajectory that is relatively close to a lamp, it will experience a relatively high fluence rate, and because it may be in the momentum boundary layer, it can also experience low velocity, thereby yielding a long exposure time. Collectively, those attributes will deliver a large dose to that microorganism. On the other hand, there are some particles that will go through the system and receive a small dose. For example, particles that don't go close to a lamp, perhaps right down the center of a collection of lamps, they'll experience relatively low fluence rate and high velocity, or relatively short exposure time. In addition, there's all sorts of intermediate conditions that may exist. Basically, this indicates that there will be a distribution of doses that are delivered by this system. Generally, the way that we account for the performance of these systems is then based on numerical simulations that involve computational fluid dynamics, a fluence rate field model, and a kinetic model. Now let's consider the dose distribution function specifically. Dose, as we've described previously, is the master variable in photochemical reactors, not time. As we've seen, the dose received by an individual particle will depend on its trajectory through the irradiated zone. Some particles will receive a large dose, some will receive a small dose, and some will be in between. The overall performance of these systems will depend on the distribution of doses that is delivered. So the image on the right is an illustration of a design of a photoreactor that was developed on the computer before any prototypes were built. So let me walk you through this simulation process based on the tools that I've just described. First, we'll start with a flow field simulation, and basically that involves drawing a schematic of the reactor of interest and then digitizing that schematic, followed by simulations of the flow field using computational fluid dynamics. Here we see a simulation of a flow field under one particular operating condition. In turn, that flow field can be interrogated to yield a simulation of an individual particle trajectory through the system. We can then map the fluence rate field onto that trajectory, and then we can calculate the dose that's delivered to a particle by calculating dose increments for each step along that trajectory. We repeat that calculation a large number of times to allow simulation of somewhere between 5 and 10,000 particles typically, and that gives us an estimate of the dose distribution. Now let's consider UV disinfection system characteristics. Process performance in these systems depends on the influent target concentration, in other words, the concentration of the pathogen or indicator organism that we're trying to inactivate, the intrinsic kinetics of the inactivation of that target, and the dose distribution. Hydraulic behavior in these systems can also be critical to their performance, especially when we consider open channel systems. These systems are typically characterized by head losses that are evident as changes in free surface profile. To address this, sometimes we use stepped channels. A schematic illustration is presented in the upper right. The red line in this graph illustrates the free surface profile, where oftentimes we'll see small changes in free surface elevation as the water flows past stationary objects. This results in a decrease in the free surface elevation. If that's not accounted for in design, then there can be parts of the water that receive little or no UV radiation, or other systems where a lamp itself can be exposed to dry air. Neither of those characteristics are beneficial in terms of the performance of the system. So one approach to addressing that, again, is the use of these stepped channels. Other approaches include the use of downstream liquid level controls, such as flap gates or elongated weirs. Another hydraulic issue that exists for large systems is the requirement to provide uniform distribution of water to a multiple channel system. Large-scale systems often involve multiple channels. That's required because there's flow variability, and we don't want to have all channels operating under conditions of low flow. There's also requirements for maintenance and redundancy in these systems. What we want to do is to promote a uniform distribution of flow among all of the operating channels. One approach that's been used to accomplish this objective is to include flow resistance at the upstream end of the system, and that's illustrated in the images at the right. In the upper right, we see a set of 7 channels that are receiving flow from a manifold that distributes water to those 7 channels. By looking at the colored image that results from this computational fluid dynamics analysis, we can plainly see that the distribution of flow among these 7 channels is non-uniform. To address that, a set of aluminum plates with holes milled into it was introduced at the upstream end of that system. This is conceptually similar to the use of flow straighteners that are applied in wind tunnels. And you can see that after those flow straighteners were introduced, for the same system, we see much more uniform introduction of flow into the 7 channels that comprise this system. Summarizing then, contemporary analysis and design of disinfection systems is based on numerical simulations. Those simulations need to account for transport behavior and mixing, disinfection kinetics, and any other reactions that could take place within the system. The contact chambers that we use for chemical disinfection, such as disinfection by the application of chlorine or peracetic acid, should promote plug flow conditions. This translates to a relatively low dispersion number and a narrow residence time distribution function. Similarly, UV reactor performance is governed by the UV dose distribution. And just as the residence time distribution for a chemical disinfection system needs to be narrow, generally the performance of UV photoreactors is also favored by systems that deliver a relatively narrow dose distribution. The characteristics of these systems, especially UV photoreactors, really cry out for applications of numerical simulations based on integrated applications of computational fluid dynamics and fluence rate field modeling.